Nisha Todorovic, who's here visiting from UIUC. He's a postdoc there with, is it with David Forsyth?
No,
or which is, of course, up on the screen. So I'll turn it over to Sinisha. Be about a 45-minute talk, and then we'll take questions at the end. Or would you like questions in the middle?
Yeah, I would like questions in the middle. That'll be easier.
So feel free to bring up questions during the talk if you have any.
Okay, thanks. Thanks, Andrea, for organizing this for me. So this is a joint work with Professor Narendra Ahuja, and I'm their postdoc. The main topic of this talk would be given an arbitrary set of images to discover recurring patterns. So these patterns, in fact, are objects in 2D, and in this particular example, we were able to extract these two patterns as the most occurring things. So one could even, just start anticipating what the entire talk is about, is that things that recur in arbitrary set of images may have some perceptual value to them. We can even relate some semantics to them. So in this case, like canonical views of a horse or any object that recurs in the object in the image set. So here's the outline of the talk. I will talk about object recognition throughout the talk. And first, I will give you the review, then some other contributions that we've made in the last 3 years. The talk will focus on unsupervised object recognition, and then in the end, we will just cover the supervised case just to show that the entire method covers both ends, supervised and unsupervised settings. So in this review, I will briefly go over the standard modules of an object recognition system, just to point out what are the main contributions to this work. So standard recognition system consists of some training images with which we usually communicate the nature of object or object category that we want to learn. Then we represent images using some suitable features, have object representation, and then given a previously unseen image, the object is either recognized or even segmented, or we even have a short sentence as an explanation, for instance, a face is in front of a board, and so on. And so I will go in the following slides over each of these modules and just briefly review what is the state of art. So current state of the art says that categories must be defined by a user. So the category must occur in every training image. And we have this kind of broad division into supervised and weakly supervised training sets, where in weakly supervised ones, we eliminate the manual segmentation of objects, but still we require labels for each image with respect to the category the image contains. And also, in addition to that, we need to prepare a background. So training images are a background category. This is an ill-defined problem because background is defined with respect to the categories that are present. So it's not defined with respect to intrinsic properties, but with properties that are not in those that we want to learn. As for feature extraction, the following module, the approaches use key points, edges, or regions, and I will talk more about the features that we use, and features that we use are regions and why, and so on. So it'll be in the following slides. As for object representation, it is widely accepted that spatial information is useful, and to encode spatial relationships between some features of an object, one may use either a planar graph representation or hierarchical graph representation. There are both advantages and disadvantages to each approach. So here I will just briefly talk about a hierarchical approach, where this is my PhD work, where the idea was to find a structure in observables in the image, and and that structure would be like hierarchical graph model, Bayesian tree, where hidden variables, in fact, represent object parts that generate the observables. And whenever we need to learn a graphical model, there are two things related that we want to learn. That is to find out what is the model structure, so how many hidden variables we have, at what level they are, how many levels we have in that hierarchy, and also PDFs that characterize each variable in the model. Learning these two things usually is computationally feasible. So people have approximate approaches, iterative approaches, and that's the one that I also propose for my PhD. In the end, we end up with some learned structure of the model and PDFs of random variables, and in that way obtain the model of the object as a forest of Bayesian directed cyclic graphs or trees. And so, okay, so that'll be just an illustration of one hierarchical model. So the main problem with current approaches is that they usually have only limited goals. So either they are just aimed at doing image classification, or just some kind of constrained set of goals, whereas object recognition has so many other things on the list, like explaining the location of an object in the context of other objects, that also we want to delineate the boundaries of a recognized object, and so on. Another problem with current methods is that they usually use approximate inference methods, because the fancy stuff that they propose to represent objects or to extract features and so on turns out to be computationally infeasible. For instance, the model that I presented just a slide ago, it has this problem. So I had to use variational inference. And whenever you use variational inference, then in a way you throw away all the nice theoretical initial start that this needs to be a nice hierarchical model where things are causal. And then with variational inference, you just break all these causality connections and treat all variables independent and so on. The MCMC also has a problem of slow convergence and so on. So what people usually do in terms of object representation to resolve these inference problems, they come up with a fixed structure. So in constellation model from Caltech, you have that objects have 6 parts. And why 6 parts? It's a magic number that they come up with. So maybe it's justifiable for faces that we have 6 parts, but then for elephants or for forest or for any other type of object, how can I claim that there are only 6 perceptually valid parts? Hierarchical approaches usually fix the number of levels. For instance, Song-Chun Zhu says that objects have 3 levels, and why 3 levels, and he cannot explain. Or maybe a branching factor. Usually you have a binary splitting of, so for instance, in pyramid approaches, pyramid is a regular structure where the image is binary split into smaller parts and so on. So this branching factor is also fixed as a power 2 number and so on. And finally, we have these problems that usually approaches require large sets that need to be labeled. This involves large human labor, and suddenly this background category is an issue. So all these deficiencies of prior work I tried to address in my work, and whether I succeeded or not, I hope you'll be happy with the solution. So here we go with the unsupervised single category recognition. This is just simplification of the entire approach, just to illustrate the main methodology used. But the most, all these techniques are in fact used to handle multiple categories, which I will eventually come to that point. OK, so what is the problem statement? Given arbitrary images, each containing more than 0 category instances, but some images may not contain category instances at all, determine if a category is present in that image set, and if yes, learn the model of the category. So it's just single category that we are after. And then, given a new image, recognize and segment all occurrences of the learned category. So this would be the setup. Given a completely arbitrary set of images, like some random things, try to see what is the pattern, what is the theme that recurs in that set. And in this particular example, the patterns are faces that are most frequent here. So we would like to learn faces. So each image may contain more than or equal to 0 category instances. And so in the set, we don't have background images. We don't have labeled images. And also, what is important, that the entire set is very small. So we want to learn faces only on 6 training images, not like 106, but only 6. Okay, so since there is no user to define what a category is for us, we need to come up with some mathematical definition. So we reason that patterns that recur in the set are, in a way, important because objects are structured, and everything that does not repeat in the image set should be cluttered and, as such, should not be learned. So things that recur and are similar in our given arbitrary image set, we call categories. And one should make a distinction that category for us, in our approach, doesn't mean a semantically well-defined category, but it's a just recurring pattern, 2D pattern with certain properties. And properties that we want to examine are photometric, geometric, and topological. Photometric would be like color, contrast, geometric area and shape, and topological would mean that if an eye is embedded within a face, that's important information. So containment is important, and also spatial layout, that the hand is usually below a head, and so on. So spatial layout relationships are also important to us. So for instance, using this definition, we might say that elongated shapes is a category, and it's a valid category for us. So we have elongated shapes in the fence and also in legs. Then other things, other patterns that repeat in this arbitrary set are also categories for us. Why not? So this is my manual segmentation. It's not the actual results, so don't get confused. This is just to illustrate the concept. So we examine these properties, and as these patterns become larger and larger, they, we believe, are gaining more and more semantic meaning. And eventually, the largest objects that have similar photometric, geometric, and topological properties, we extract, and it turns out that they really mean something meaningful, so perceptually valid. And I will show that in the following slides. This definition is recursive, which means that a more complex category can be expressed in terms of its subcategories. So if I have a category horse, then a subcategory of horse are legs of a horse. And then I have a cow as a category, and then the subcategory of a cow is a leg, and then legs of horses and cows can be shared. So we want to capture all these relationships. OK, so that's the setup. So the training set is arbitrary, and then the following module is feature extraction. So we believe that using regions is good, and it has its advantages over using key points and edges. Regions facilitate modeling of fundamental characteristics of objects. Objects are cohesive, and I want to capture that information. I cannot capture it by just random points. Next, I want to capture the information that I is contained within a face. And this containment cannot be encoded by key points. Regions are higher dimensional than these local features, and in a sense, they include edges. So if somebody is like a great advocate of using edges, you might as well use regions, because region boundaries give you edges. And also very important for our goals is that once you discover a right configuration of regions that are features of your object, you immediately get recognition and segmentation. And why? Because region boundaries coincide with object boundaries or object part boundaries. So you don't not only get the segmentation of an object, but you also get the segmentation of its parts and its subparts and so on. So that's the motivation for using regions. But the problem with regions is that low-level segmentation, which gives us regions, is usually unstable. So in this particular example, we have like two exactly the same persons and completely different segmentations. So the community is usually, that's my sense and my interpretation, kind of afraid to use regions, although all of us are aware of its advantages, but just because how to address this problem. This is a huge problem, but then we just reasoned that if we somehow manage to address this problem, then we will gain all the advantages of using regions. So one should not go away from regions just because there is this problem of instability. If you have a top-down information that can guide your algorithm, your recognition algorithm, and address this instability, then you will get a very powerful feature representation of images and your object. So what is the problem with this instability? That adjacent regions may split and merge. So in this particular example, we have a large region for like this side of a face, and it got split into two here regions and so on. So this splitting and merging is, in fact, how the instability, in fact, represents itself to the algorithm. So, our way to address this is exactly to explicitly account for splitting and merging of regions. So here we have a slide that illustrates our image representation. So we use low-level segmentation to give us regions. Low-level segmentations finds homogeneous regions. But then you may ask, how do you define homogeneity? Homogeneity is defined as like the level of variance of, for instance, intensity of pixels within the region should be less than a certain threshold. Where to set the threshold, nobody knows. So we just use exhaustively all possible thresholds from 0 to 255. And so we get a multi-scale segmentation where at each level of contrast, we get a segmentation. So all these regions that we generate can be organized in a tree structure where a larger region contains smaller regions that are embedded within it, and so on. So this would be a segmentation tree, which where each node is a region, and hierarchical links represent embedding of regions. So since each node is a region, we can associate a list of region properties like contrast, area, and so on to each node. And these properties we define relative to parent properties to achieve scale and rotation in plane invariance. So for instance, area is not 50 pixels, but it's a percentage in the parent area. So like an eye, so if a face goes through changes in scale, you don't want to capture the absolute area of an eye. You want to capture the ratio of an eye and the face through scales. In addition to capturing hierarchical relationships, we capture both like spatial layout relationships. Since we use regions, intuitively, it's not quite clear how to define neighbors for regions. And in this slide, I illustrate a case where these two regions are close to each other, and yet they see each other only through a gap. And perceptually, they should not be declared as regions. Whereas these two are even farther away, but since there is no narrow gap between them, they should be, in a way, regions because they are close to each other. So region-neighborhood relationships are difficult to define, and they depend not only on distances between regions, but also on the spatial layout of other regions in the neighborhood. To capture that configuration of regions, in a nice way, rigorous, like mathematical way. We use a Voronoi diagram that we generalize for regions. So Voronoi diagram is, yeah.
Can you explain what the nodes and edges in this graph?
OK, so blue would mean a region. And red would be exactly that I was about to explain, Voronoi polygons over regions. So black tiny lines depict Voronoi polygons for each pixel along the boundary. Since regions are exposed to each other via their boundaries, it makes sense then to compute generalized Voronoi diagram over boundary pixels. So I don't care about pixels inside the region. I just care about pixels on the boundary. I compute for every possible point here a Voronoi polygon, and then find the union of all these small polygons, and that will be generalized Voronoi polygon. And then if two polygons share a part of their boundary, their neighbors. And then, so I can use Voronoi diagram to define the neighborhood relationships, but at the same time, I can also measure the strength of their relationship. So we do that asymmetrically. The strength viewed by this region would be the length of this shared part divided by the perimeter of the entire Voronoi polygon. And the same here, but since the perimeter here is smaller, so this region would find this one as a more important neighbor than this larger region for this one, which is intuitively kind of justified. Like that if I have a large region and there is a small region in its neighborhood, it may not be as important. Whereas I have a small region and a big region next to it, so it should be more important too, seen by this one. So this is our CPR08 paper, how to also define neighborhood relationships between regions. And then given our segmentation tree, we establish neighborhood relationships among sibling regions and get a graph structure. So each node is a region, and the structure of the graph defines the relationships. So it's a rich representation that allows us to do a lot of things. So what we want to do to discover repeating patterns. And these patterns, in fact, appear as many similar subgraphs in our image graphs. So how to detect them? To discover them, we do graph matching. So the idea is to find common subgraphs in the image graphs. In this particular case, given two images with two faces, we managed to match them in this way. And matching also gives some random clutter, but this is OK. We will be able to eliminate that if this clutter doesn't repeat in the images. And if it repeats, then it should be associated with a category that we learned. So if a face always appears in front of a blackboard, then blackboard together with a face should be a category for us, because we don't have any supervision to make a distinction between the blackboard and a face. OK, so how to do matching? The main idea is to match regions in these two graphs if their intrinsic properties are similar. And intrinsic properties, by that I mean color, shape, area, and so on. Of course, all that relative to their parents. And again, the same should hold for their subregions. And the same should hold for their neighbor regions. So it's optimization over intrinsic properties and hierarchical and neighbor relationships. And the result, the actual common subgraph that we obtain, should preserve original topology of the image graphs. So matching is the place where we address instability of regions. I certainly would not have time to explain all the details in 45 minutes of this talk. But the idea is that because we have splitting and merging of regions, you may not expect that region in one graph should match only to one region in another graph, because this corresponding region may be split by the segmentation algorithm. So you want to allow many-to-many matching so that one node can match many nodes in the other graph and vice versa. So you want to have one-to-one, many-to-many, one-to-many, all these combinations. So to do that, we augment each graph by their mergers, and there is some nice way how to do it. It's not like exponential that all possible combinations we augment, but I don't have time to explain that. And again, since due to changes in scale, some parts in this subgraph, for instance, here, I is on the, for instance, third level, and there up I is on the fourth level. So I want to achieve matching so that I'm not fixing that regions at the same level are bound to match. I want to allow flexibility that different regions at different levels can still match. And to do that, I introduce these auxiliary links that would guide the search algorithm for good matches by introducing transitive closure of the entire tree. In the end, I get this. So if you notice, this face here was split into 3 parts. And because of a merger, we managed to match this good face with this one. So at the root of this result, this would be an example of one-to-many matching. The node here, 1, that represents a face, matched these 3 nodes here. So we got a nice matching result. This would be like the formulation of the matching algorithm. Given 2 graphs, find the bijection, which is a subset of the Cartesian product between the sets of 2 nodes, 2 node sets of 2 graphs, so that the initial topography is preserved, and also we get the maximum similarity measure between the 2 graphs, where this is the function certainly heuristically defined, because at this low level of extracting information, we don't know what the face is and whether there is a face in the image. So, how to define this function, what is similar, is certainly at this level heuristic. OK, so I don't have time for this. This is a detail how the matching actually works. And those who are interested can just read the IGCV paper that recently got published on that. Complexity is n squared, which we would like to reduce. But any reduction would involve higher level information. So it's a problem. This would be an example of our results. So given 2 graphs and their hierarchical and neighbor relationships, we match both regions and we match their relationships. So this is the end result that we have. OK, so finally, once we have the similarity measures computed for each possible combination of nodes and their subgraphs, we need to extract the most useful information. There are various ways to do that. And in each paper that we have published so far, we have a different way to do that. So in this particular example slide, I just showed one possible case, and that is to just plot a histogram of all similarity measures between all possible pairs of subgraphs in all possible images, and then compute the frequency of this particular measure, and then extract the mode that is most prominent. If mode exists, it means that categories are present, which means so similarity measure is high, so subgraphs are similar, and at the same time, their frequency is high, so something similar recurs in the image site, so this is what we are after. And so most similar and most frequent bunch of subgraphs should be our extracted category. And this is the result that we get. Finally, once we extracted instances, patterns that repeat, we need to learn their model. So it's a question of how to learn a model of structured data. Usually, what people address is to model like vectors and things like that, but how to find a good model of a bunch of graphs. So our solution is to do graph union, because sometimes the face or any object in question can be occluded, so I may have detected only a part of that object. Also, due to instability of segmentation, some parts may be missing. So the best idea is to just join all these graphs into the union. And this is just a symbolic representation of learning a graph union. We align all these graphs like this, and then project them into a structure like this. So graph union would be like the union of all these subgraphs, where one parent may have a lot of children and one child may have a lot of parents. So this is not a strict tree structure, but just a DAG. I avoided depicting the neighborhood relationships because the picture will be quite cluttered. So you just visualize. So imagine that we also learn neighbor relationships here. So this would be our structure of a model representing faces in this case. So to get back to the beginning of this talk, I explained, so for my PhD work, I had this hierarchical model where I would have to learn simultaneously structure and PDF of variables in the model. So the work with these graphs and everything that I presented so far would amount to that structural learning. So what I did what I did in my postdoctoral work is to avoid the computational difficulty of extracting a structure of a graphical model, use graph theory to do that, and then once I have the structure, then I have a very simple problem just to learn PDFs. So given a structure of my model, I just can just learn some joint PDFs on that structure. Each node represents a cluster of all possible regions that I extracted, and the PDFs of that cluster is easy to compute. And so on. So given a previously unseen image and the model, we match them and get these results. So matching the graph representation of the image with the model that we have learned gives the simultaneous recognition and segmentation. So I avoid all these post-processing steps that usually are present in the state of art, that once you detect an object, then you kind of develop these probabilistic maps and over the location of an object. Then you need to threshold these probabilistic maps, and nobody guarantees you that the thresholds that you learned on training sets are the same as in the test image. So this gives us more valid object boundaries. This is an illustration of a model that we learned for Weismann horses. So given an arbitrary set of images in which horses appear, and suddenly horses are in different poses, this illustrates that we can handle articulation, some small changes in rotation, and certainly scale. And this would be a result. So these are test images. By matching the images with a model, we get immediately segmentation recognition. And segmentation is good on jagged blurred and other usual challenges that are encountered in object segmentation. Parts where we miss to segment are low contrast, obviously, regions where the initial low-level segmenter didn't even give us the boundary. So this background is, kind of eating up the part of a horse. So that's why we couldn't even, get that edge of a horse. So low contrast regions that merge with the background is still a problem for us, but we are trying to address this problem. That's a problem related to the segmenter, low-level segmenter that we use, but not inherent to the high-level things that I presented. OK, so the same methodology can be used for addressing texture analysis. So this will be very brief. I don't have time to go over the details. This is our ICCV07 paper based on the idea that texture represents a repeated spatial repetition of some texture elements that we call texels. So what people did in the past is just to locate these texture elements and represent them as points. Texture elements are usually very simple. These are like templates, like polka dots or some rectangular, very simple things. And what approaches require some constraint in terms of placement of texels, either they are regular or near regular. We address a more complex setting. The texels are real objects with some structure within them, subtexel structure. Texels may occlude each other. And so the problem statement here is to, given an image of a texture, we want to identify texels, learn their model, and given a new image of the same texture, try to segment out the texels. So the contribution of this paper is that we were the first to segment out texels. This problem is difficult because, if you can see, we need to learn a model from only partial views so we need to learn the model of the entire texel from only partial views of a texel. Well, certainly some texels may have been fully visible, but some of them are partially visible. But in general, we can do that if there is no texel that is entirely visible. We can learn that only from partial views. These are the results using the same techniques that I have shown. And this is, I would say, the most impressive one. Some of the B's we miss just because of this low contrast. We still have that problem with the low segmenter. So just given this arbitrary image, we don't know what the image even represents. We just know that it's a texture with some repeated elements. We try to search for similar subgraphs of the image graph. And this is the result that we get. Finally, multiple category recognition. So the training set here is more complex. We have multiple occurrences of multiple categories per image. Certainly, category instances may experience variations in scale, viewpoint, and illumination. We want to address articulation, self-occlusion, certainly clutter. And again, it's an arbitrary set. So in some of the images, we may not even have category instances, so 0 occurrences. Categories are not defined by the user. They are unlabeled. And again, we have a very small set, let's say 10 images. So on 10 images, I want to learn horses if they repeat in the set, or cows if they repeat in the set. Or in this case, since in every image you have like a rider-horse combination, I may have extracted only a rider-horse as a separate category. But I will explain how then to handle that case. So, problem statement: given an arbitrary set, we discover all categories present, learn their models, and then given a previously unseen image, we detect, recognize, segment all of that together without any post-processing steps. So this is simultaneously done. But I think the most important contribution of this work, this is ICCV07 also, that we are able to give a semantic explanation of recognition. So standard approaches, they just label, OK, there is a face, or there is a horse in the image. But we are able to summarize what we see in the image. We can give a short, brief sentence that says, in this image, we recognize a rider-horse. Why? Because there is a horse and a rider in the image. And why? Because there is a tail and legs. And legs are shared by cows and so on. And there are some unshared parts like horns and so on. So we can give, by our representation that I will briefly explain in the following slides, what is shared, what is not shared, what is detected, at what level of hierarchy is detected. So we can give an explanation in terms of, so explanation of recognized categories in terms of simpler subcategories. OK. So this work questions what is the most efficient model of multiple categories. So if we want to handle thousands of categories, what will be the best way to have their representation? And there are various approaches. I will just skip them. So what we want to do is to capture the fact that usually objects can be viewed as configuration of parts. So parts can be shared. So that's another thing that we want to capture. So horses here and cows share legs. And camels may share legs with cows and horses. But there are things that are not shared, like humps and like heads. And so this representation is efficient because usually object parts experience smaller variations, so their learning is more robust. And also they occur more frequently in the world. So legs occur more frequently than horses by default. So it's guaranteed that the model would be more accurate when you learn horses because there are more available of them, so more data available. Another thing, sharing of parts allows sublinear complexity. So if you want to learn a camel, you don't need to start learning legs from the beginning. You can just add more and more complex categories, and you can have already learned parts and attach them to. So this model may not be learned like in a batch approach. It can be learned online. As you add more images, you can just augment the model and so on. Unshared parts are important for the follow-ups. Again, the model is completely arbitrary structured. We don't fix the number of layers. We don't fix the number of parts, and so on. And we certainly have exact learning of structure. We don't use any MCMC or approximate inference. So, OK, so this is just an overview. Given like a set of images, we represent those images as graphs. And then we discover similar things in them, cluster them, and then extend the neighborhood and hierarchical relationships between regions to the relationships between clusters. So this cluster would mean a node in this grammar of categories. And since legs are embedded in this cluster, so these legs may be embedded here, we then extend the link. And that's how we construct the model. Again, given a previously unseen image, by matching the image with the model, we get immediate recognition, segmentation, and also explanation. So here's just illustration of results. This is a training set of UIUC hoofed animals data set that I prepared. It's available on my website. The set has 6 major categories like deer, cows, horses, and these sheep. And so these categories are very similar. And in a way, this data set complements standard benchmarks because it has like images containing very similar categories. So it requires the system to have high resolvability between the categories, which is a difficult thing to achieve. It's very easy to make a distinction between a face and a piano, but how would you recognize like a house and a cow? How can you just discriminate between the two categories? So it's a difficult problem. These are our results. Some of the animals we miss. Why? Because their subgraph does not set off that threshold of recognition for us. But if we tweak that threshold, put it up and down, then we will be able to even recognize these parts. For instance, dogs have never appeared in the training set, but we are still able to recognize dogs' legs. So if my threshold of like false alarm and recall and whatever threshold we use for this recognition, if it were a little bit lower, then we would just say, OK, we recognize legs. And then like by using that information, we could maybe infer that there is some other animal that we were not able to learn from the training set. And so these are some of the results. Again, the leg here is missed because of the low contrast with the background. And certainly, the model learns on shared parts. These are some, just quantitative results. On this data set, we achieved recall about, in mid-70s. OK, so this is another application where the entire approach can be used. This is our new ECCV submission, just to illustrate the full power of it. Given randomly extracted frames from a video sequence, we were able to summarize that video sequence. Since the model is generative, we can just synthesize, project each node as a region. And so none of these instances occurred in the set. We probabilistically synthesize these objects that are learned from the set. If you can see, dogs has never been fully observed, and yet we were able to kind of learn an entire object as a dog. So the question here, why do we learn 4 categories? It's our level of sensitivity to the differences between categories. If our level of sensitivity were a little bit lower, we would have learned one node for all possible poses of a person. But in this particular example, we used a very high sensitivity level. So that's why we learned 4 categories in this particular image set. Another example, that a bunch of images that this is a video of a man dancing. We can generate a 2D sketch. So if you can see, none of these poses appeared in the original frames. But we probabilistically generate the most probable pose of a category that we learned. Again, for instance, these 2 guys never appeared together in none of the frames. But we summarized it. We learned that these 2 should appear. And again, due to regions and their hierarchy, we are able to produce summaries of different length. So if somebody is interested only in the high level, just abstraction, we can generate this type of a summary. This would be like one possible summary. This would be the second summary, and so on. But we can increase the level of detail that we put in our summary. But by that, we also increase the length of the summary. So we can change these parameters. OK, so again, so finally, this part of the talk would be to address a supervised setting. So far, I've been talking about unsupervised extraction of categories and their learning. So what actual results we achieve for a supervised setting, just to compare the entire method with the standard methods that are supervised or weakly supervised. So this is our CVPR08 paper, which deals with the problem of supervised image categorization. So these 2 categories of images are examples from Caltech 256. This category is labeled a horse, and this category is labeled a wagon. And as we can see, it's very difficult to classify. So given an image, how can I say that this is an image that belongs to this category, or this is an image that belongs to this category? And why? Because there are a lot of things that are shared between these categories. So in this particular set, horses are prominent. But here also, horses are prominent. So I'm stuck. Then wheels are here, and also wheels are here. But what is not in this set of images is those unshared parts that I learned. And this would be the wagon top. Since this test image doesn't have a wagon top, it is correctly labeled as a horse category. So we learned, so in this paper, we present an approach how to make use of the model that learns shared and unshared parts, and how to weight the relevance of each part to the recognition of their parent category. So this would be results on a Caltech 256. So so the latest result is from Zisserman's group. So we increased their performance, published at ICCV 07, by 9%. And this would be our result for Caltech 101. So not only that we improve like on 30 categories, but also like for every possible number of training examples per category. So, so the entire approach obviously is good for unsupervised approaches, but also for supervised settings. Summary. So to speed up the entire summary, like the main message that should be taken from this talk is that regions are good. Regions allow us to have rich representations of images, and these representations can, encode, capture spatial relationships like photometric, geometry, properties of objects. But when you use that kind of representation, one needs to overcome the associated problems with segmentation instability. But once you overcome that, you have all the power that you can get from regions. And the power is that you may learn perceptually valid categories from completely arbitrary sets. You can have nice summaries of videos. You can have variable length summaries. And at the same time, if somebody wants a supervised case, which is valid, for instance, in a surveillance video, why would you want a method to account that there is a possibility for dolphins to occur? That's maybe unrealistic. So in a more constrained settings, this approach can still work because supervised setting is quite valid and real. OK, and again, we can suddenly extract texture elements called Texels. I showed you only the example of a frontally viewed texture, but the same approach can be applied to different views of a texture, and that's our future work. So, thanks to Narendra Hujak, who is my advisor, and so on. Thank you. So, any question?
And we'll pass the mic around for questions.
I'm used to seeing 2.5D to signify a representation where you have images that have occlusion priority, but they also, in general, have scale. Do you call this 2.1D because the Texels don't scale?
2.1D was named by David Mumford like in the 80s, and it is a case where objects are thin plates that are, and they're overlaying each other on the surface. So this gives us occlusion, but there are no 3D effects because they are thin. And by thin, I mean their width is smaller, so much smaller than the distance from the camera, so the 3D effects can be neglected. So I ignore shadowing effects and like like these 3D effects that come out from occlusion of real objects.
So I'd never heard of this formulation. I'm kind of curious. How is Mumford's 2.1D idea distinct from Matherin's dead leaves models from the 70s?
That's exactly that. He called that, so dead leaves model is 2.1D, yeah.
So I was just wondering, could you apply the same framework, like say, if I didn't want to rely on segmentations, but I wanted to use local features, whatever, could you do that?
Yeah. So the entire approach, I must say, relies a lot on topological information of features. So the fact that something is embedded within a larger region is very important. And that allows us to handle like small training sets. And for instance, for faces, we are able to learn the entire category of faces only on 6 images because topological information is very important. I don't know how to capture topological, that kind of information with points. Again, spatial relationships are, with points are defined only with respect to their distances. We believe that regions give us better, more perceptually valid neighborhood relationships because neighbors are not just neighbors because they are close to each other, but because also the neighborhood allows it to be neighbors.
Could you elaborate a little more on the graph matching approach that seems to be the crux of the why this works.
Yeah.
Right? So what is good properties of the initial segmentations that you start with? How do you overcome, which constraints help you exactly overcome the fact that the regions are so unstable? Like during matching, do you have extra hierarchical, transitive properties? Do you have issue? A little more along those lines.
Yeah, so there is a large, volume of literature on image matching, where images are represented as graphs. So it'll be difficult for me to just to give a crux or short course on that. But the main idea is to. Okay, so let me go to that slide that I skipped a little bit. Just, so in this particular example, so suppose we have an ideal case. So just ignore for the time being instability of regions. So given two possible graphs, we want to match them. So this is so how to do that? You need to find good pairs of regions. So what I do, I form association graph, which is like all possible pairs, combination of pairs. Like rows would be nodes from one graph, and columns would represent nodes from another graph. So you form a matrix of possible pairs. And then, since this matching needs to preserve original topology, you allow connections between those pairs that preserve that topology. So in this particular, let's say, example, V2 and V1 are a valid match. And also, this is a valid match because V3 is a child, and V3 prime is a child. So if a node matches, then their children should also match. And by that, you allow possible, combinations of matches. Other things, this combination is not connected because it will violate the original topology. Once you have this association graph constructed, then there is a theorem that the matching result is a max clique on this association graph, and it's straightforward. Max clique is an algorithm that requires n squared. And why? Because I start with the association graph that has n squared nodes. Yeah. Yeah, max clique, there is no exact algorithm for max clique, but unlike MCMC and other approximation algorithms, there is no approximation. It converges very fast to a solution that is global. So it's solving a complex convex problem. So it's guaranteed that it'll end up after a certain number of iterations to a global solution. Yeah.
Hi, I have a question about, you said topological information is really important in your model, but for the case of the animals, the background is almost always the same. They always stand in a grass field. Why doesn't the background become part of your model?
So I didn't show the entire model. You learn definitely other nodes which represent some parts of the background that do repeat. So in images where there is no grass, this information helps you to say that there are things that are unshared between a grass-cow combination and a cow. And then that's how you can extract that cow is different from grass-cow combination. And since we learned the frequency of occurrence of grass-cow combinations, since this combination has lower frequency, then it's not extracted in that histogram. So that's how I eliminate. So just pure on frequency of co-occurrence of different categories.
And I think that's all that we have time for. Let's thank the speaker again.
Yeah, thank you.